Hi, everyone. Welcome. My name is Ayla Pamukchu, and I am a professor here at Stanford University. So welcome to our rock tour today. We're going to take a trip around Stanford University and take a look at some of the rocks here and, maybe take some observations and take a look at things and learn a little bit about the geology of California, actually, because many of the rocks here on campus are from California. So before we get started, I'm going to just let you know, I'm going to have the chat open. So this whole time, so you can put, thoughts or ideas or questions into the chat, and I'll try to answer them as we go along. And as we get to some of the rocks and try to make some observations, we can try to unmute and say those observations out loud if you want. So with that, we'll go ahead and get started. And the first thing that before you go out on a geology trip, no matter what you want to do, is you want to make sure that you have all of your supplies with you. So I have my handy dandy hat because it's sunny out, and I'm going to switch my camera around so you can see the other tools that I have in my field bag. I, of course, have my notebook. So this is a really important part of what we do as geologists. We have our field notebooks, and this is a particularly special kind of notebook because you can write with it in the rain, in the water. So we can take it out into the field. You see it gets really messy, and we can write in it. And even when it's raining out, we can actually take notes in it. So I have my field notebook, and I have my pen. I have my sunglasses because it's sunny outside. I have this thing here, which is called a hand lens. And what it lets me do is it's like a little tiny magnifying glass, and it lets me look at things, very small things like crystals in rocks, very up close. So I have my hand lens. I have my phone or my radio or my other communication device in case I need to call somebody for help and safety. I have my water bottle, and of course I have my snack, which today is apples. So I'm going to go ahead and pack my bag, and we can get started. In the meantime, if you have any questions, go ahead and ask. So like I said, I'm a professor here at Stanford, and I study geology. In particular, I study volcanology. Does anybody know what a volcanologist studies? Vulcans? Close. Volcanoes, that's right. Somebody said volcanoes. So I study volcanoes. I specifically study really gigantic, humongous, super eruptive volcanoes. These are volcanoes that we've actually never seen erupt in human history. So they're things like Yellowstone has historically had super eruptions. All right, so I've got my bag packed, I'm ready to go. Let's take a look. So we're going to start out by taking a general overview look at one of the main buildings on campus. So this is the main quad of campus. This is one part of it. And the quad is made out of this really brown stone. Any guesses on what this stone might be? A brown rock. What kind of brown rock this might be? Somebody says granite, somebody says limestone. Good ideas. So this brown stone is something that we call sandstone, and it makes up most of the main old part of campus. So we're going to go a little bit closer and start to take a look at this sandstone. When I say the word sandstone, what does it make you think of? Beaches. Somebody says beaches. Yeah, why do you say beaches? Some stone made of sand. That's right, that's exactly right. So if we get closer, let's see if I can find a better lit spot, I'm not sure. You might be able to see it's a little tough. You might be able to see some little grains that look a little bit like sand. But this is a rock made out of sand. So it's a bunch of sand that's been smushed together really, really hard. And that is how we form a sandstone. But since it's made of sand, And somebody said it makes them think of beaches. Where do you think sandstone is formed? Beaches. So somebody says that they think it's made on beaches, and that's right. Sandstone forms where oceans were, and there are sediments and beaches and sand all over the place. So somebody here asked, if it's made of sand, how is it held up so well over the years? That's a really great question. And the reason is because unlike sand, right, it's a rock. I can't actually pull it apart like pieces of sand, but that rock is formed when the sand from the beaches sits underneath, it gets kind of buried, and that kind of compresses it all together, and you get the sand that's turning into a rock. But it's hard, right? That being said, there are processes that can disintegrate it, that can make it fall apart. And that's called a weathering process. And sometimes that can be because you have water there and it's rolling over a rock, and that can weather it. Sometimes it's wind. If it's really hard winds for many, many, many years, that can also chip away at it over time. So even though it's not as falling apart like sand is, it still has the ability to eventually fall apart through time. It just takes a really long time. So this sandstone, I'm going to see if I can find my picture for you to show you where this sandstone comes from. Hold on one second while I put my pad down to find my tape. Another important thing to bring on in your geologist backpack. All right, let me find my map of California. Keep it to the wall for you. All right, so this sandstone actually comes from very, very nearby. So here we are in California. Here's Stanford University in the red star. Here is San Francisco in the gray circle. And here's what's called the Greystone Quarry. And this is where the sandstone came from. So Greystone Quarry is about 45 minutes south of Stanford. Now, Stanford itself was built in the year 1891, or it opened in the year 1891. So in order to build this quad of Stanford, we actually had to, there was a rail line that was built specifically between Stanford and the Greystone Quarry. And people would travel back and forth between it every day, bringing these blocks of sandstone back to Stanford so that they could build these buildings. Now, this is where the Greystone Quarry is, and this is where Stanford is, and we're currently on land. But we said that the sandstone is formed on beaches. So what do you think that means? Where was Stanford and where was the Greystone Quarry back when this sandstorm was formed? Any ideas? Somebody says on San Francisco Bay at the bottom of the ocean. That's right. It was at the bottom of the ocean. Let me find my other map here. Yeah, so back in the day, so now we have our map, and here you can also see the Sierra Nevada mountains. All of this area was actually underwater back in the day. The beach was at the bottom of the Sierra Nevada mountains. We would have been having to live in a submarine if we wanted to actually be exploring where we are today. But eventually the land got brought up and all of the water receded away. And so now we have sandstone up here on land that we're able to quarry and bring with us and build buildings out of, which I think is pretty neat. All right, so that's our sandstone, and that makes up the main part of the quad. Does anybody have any questions about the sandstone before we move on? Does anybody know how old the sandstone is? Any ideas? No guesses? Over a century, I see. So that's over 100 years ago. All right, so the sandstone, so here's our geologic time scale. I'm gonna put a picture of that up for us. So here's our geologic time scale. So here we are on the surface of this, okay? That's us. Now, this sandstone formed 37 to 58 million years ago. That's an incredibly long time ago. That's here in this period called the Eocene. So in geologic time, this sandstone was formed in the Eocene, which means between 37 and 58 million years ago, Stanford and this area was all underwater. And eventually it was brought to the surface for us to see, which is pretty crazy. It's a very, very long time ago. All right, other questions about the sandstone in the meantime? If not, we will move on to our next stop. All right. How did they carve designs into it? Good question. So the designs that you might be talking about are like these here, or maybe you can see on the edges of these things. So basically, I think that what they did here was they used some kind of mechanical chisel in order to do that. So somebody asked, can you see fossilized sea creatures in the wall? Great question. Great question, because when you walk on beaches, what do you find? What do you see when you're walking on beaches? You see shells, right? That's right. And you see other kinds of sea creatures, right? Like seaweed, all that kind of stuff. And all of that can get buried and stuck in the sand and become fossils in sandstone. So does anyone want to look at this and see whether or not, do you see anything that looks like a fossil? Anything that looks like crabs or seaweed? So this is actually very fossil poor sandstone. They've had a really hard time finding fossils in some of this, but there is one type of fossil that they do find, that they have found. Looking for my picture of it. Whoever asked the question was thinking about it. It's called a turritellid mollusk. So maybe you've seen shells before on the beach, but these are turritellids. Turritellid gastropods. And so some people have actually found big molds or fossils of these shells inside some of this sandstone. How strong is it? Good question. Good question. So sandstone is made out of the mineral quartz. And quartz, if you have ever heard of the Mohs scale of hardness, quartz has a hardness of around 7. And so, so sandstone is probably going to be somewhere around the hardness of quartz, but it will be a little different because it's not pure quartz. All right, we're going to move on to our next spot now. And this is what's called a retainer wall around one of our buildings, and it's made up of a bunch of rocks. And these are pretty grungy looking rocks, but I'd like to hear what you guys think. What do you see when you look at these rocks? Can you make any observations? Anybody notice anything in these rocks? Okay, somebody sees all types. See some stones. They make a wall. Somebody suggested that there's conglomerate, some quartz, some plants. That's right. So there are a lot. These are pretty grungy looking rocks. They fit together like puzzle pieces. Right. Somebody has chopped up these rocks or carved up these rocks and put them together to kind of make a puzzle piece out of them to make our wall. Right. So we have a wall here. But what these rocks are, so what color is this rock that my finger is on? Can anybody tell me what kind of green? That's right. So this rock is a rock called serpentinite. Serpentinite is actually the state rock of California, and it forms when you take a rock called basalt. So this looks more like basalt, it's black, right? And you actually subject it to heat or to pressure, you bury it deep in the ground, or you subject it to water. And when you subject it to water, it kind of alters it doesn't alter the composition of the rock, but it alters the minerals in the rock. And so when it alters that, it creates new minerals. So it goes from this black material into this green rock instead. So it goes from basalt to serpentinite. And it creates these, it's what's called a metamorphic rock. And basalt is a really common rock. Does anybody has anyone seen basalt before or seen pictures of basalt? Know where basalt comes from? Somebody said Hawaii, that's right. So on Hawaiian volcanoes, where we have eruptions, we get this dark black rock called basalt. Now, the main place that basalt forms is actually under the water in the ocean. So we have these different, most of the volcanism on Earth actually occurs underneath the water, and it creates these things called pillow basalts. They're these little lava bulbs that come out, and they look like pillows. And so when the pillows are under the ocean, what are they interacting with? Like bed, yes, like a pillow. It's not as soft as a pillow on your bed, but it has the shape of a pillow on your bed. Yeah, so somebody says basalt represents 70% of the Earth's crust. That's right. So somebody said it's interacting with sand. That's true, there's sand on the bottom. What else is the rock interacting with? Water, that's right, it's interacting with water. So that's the kind of metamorphism that's going on, that's turning our basalt into serpentinite. Is basalt like obsidian? Yes and no. Basalt is it's a magmatic rock. It comes from a magma, it comes from a volcanic eruption. And when volcanic eruptions happen, the magma interacts with the air and it gets cooled very, very quickly. And so when magma gets cooled extremely quickly, it doesn't actually have time to turn into crystals. And because of that, it actually turns into something called a glass. It's just like the glass that makes up your window panes or other kinds of glass. And this glass can sometimes be black, it can sometimes be red, but that's what we call obsidian, is volcanic glass. Okay? All right, any questions about this metamorphic rock before we move on? Oh, I forgot to show you the map. Let me find the map of where we are now. All right, nope, that's not the right one. I don't have my map, oh no. Okay, so let's take a move on to our next spot if people don't have any more questions about our serpentinite. All right, so now we're walking up this hill, and we're walking towards a building called the Mitchell Earth Sciences Building. And this hill is actually here because the earth beneath us has been folded and it's made these ridges. And we've built on top of one of these ridges. Okay, so now we're going to go down and take a look at some rocks that are down here. Anybody see anything interesting in this rock? Uh-oh. Looks like I might be frozen. Is it any better now? Excellent. Okay, somebody says little pieces of rock in it. What else can you see? Patterns. We see somebody says big rocks, granite, crystals. That's right. Here is a crystalline rock. So it looks really different from that sandstone that we were seeing before, right? So somebody says, is it smooth? It's smooth because it's been cut and polished. So but if you were to find this rock in the field, it wouldn't actually be this smooth. It would be more like this side of it. So this is really what you would see in the all kind of, in order to see what side of it, we've cut and polished it so you can see all the different interesting things in it. So here we have really big crystals formed in a volcano. What happened is that a magma was generated deep in the earth. And sometimes we said rocks erupt, right? But other times they don't actually erupt. The magma is inside the crust and they don't actually come to the surface. And so when that happens, it gives a really, really long time for the magma to cool. And so the longer the time the magma can cool, the bigger the crystals can get. So these take pinkish crystals, and you can see in some of them, let me find a good example, I'll try to get closer. Maybe you can see in this one here. Do you see that there are little rings inside of them? Can anyone see the rings? Yeah, so that's what's called zoning. And that's when crystals grow, they grow kind of like trees, and they develop tree rings, or things that look like tree rings. You can see it also maybe in this one. And so these zones can tell us all kinds of things about the formation of this rock. So this is a rock called a granite or a diorite. And this granite diorite is from, let me find my map. It's a little tough only having two hands. Oh no, where's my map? Aha, this granite diorite is from these Belmar crystals have also what other colors of crystals do you see? All right, let's see if I have a better connection somewhere. Hold on. Is it any better now? All right, so when we look at this rock, is it still frozen? Is it better? What other colors do we see? So we saw those pink crystals. What other colors do we see? Any other colors? Gray, two shades of gray, that's right. So those are other kinds of minerals called, we have amphibole crystals, and we have quartz crystals, and we have another feldspar crystal called a plagioclase feldspar. So in this rock, we have feldspar, we have alkali feldspar, which are those giant pink crystals, we have quartz grains, and we also have amphibole or biotite. All right, we're gonna try this one. We'll see if the connection stays steady. What do you notice about this rock? It's shiny. That's because it's been cut and polished again. Striated. Smooth, yep. Let me show you the side of it, because this is what it would really look like if we were to find it out in the field. So it's not quite as smooth and shiny. Lines, yeah, so these are all kinds of lines that form. Let's see if I back away from it, maybe it will be more obvious. You can see all kinds of wavy lines that are forming, and that's because this is a metamorphic rock. So this is a rock that was put deep into the earth, and it was and that pressure and the heat that it encountered deeper in the earth actually created this metamorphic rock, and it creates these strings that occur, these kinds of layers that we see. And so this is what we call a schist, S-C-H-I-S-T. And it formed in what's called a subduction zone. Let me see if I can get so it formed when we had the ocean going underneath the continent. And you can see that it goes down underneath. And what happens is that it experiences high temperatures and high pressures. It gets buried very deeply. And that causes the rock, the basalt, to turn into a different kind of rock. All right, questions about this? Otherwise, we will move on to the next part. And this rock, the schist, actually comes from Marin County, so just north of, all right. So now we're gonna move to the other side of the building. Am I still frozen? Okay, good. Let's try taking a look at this rock. So what do you notice about this rock? Any observations? So somebody thinks it's got some gouges in it. There is a green sticker at the top. Take a little bit of a walk around. Does it look like any of the rocks that we've seen before? This rock. Yeah, so it looks a little bit similar to that granite diorite we were seeing before, right? And this time we have a big, huge section of it with these really, really enormous crystals in it. So these crystals are in a vein, right? They kind of make this line through this whole rock. And that vein is what we call a pegmatite. Somebody asked, is it a table and a rock? It is a table made out of a rock. That is what it is. And so this pegmatite forms when we have hot water going through the rock. So we have that granodiorite material, and it has this big, huge vein running through it with these really, really gigantic crystals in it. So you can see some of them like these here, right? These are feldspar crystals. What do you think this grayer material is? Any guesses on what this gray crystal is? So this is a huge crystal of quartz. This is quartz that's been rimmed by a bunch of feldspar crystals, okay? Now, when we go and we look at what we describe as finer grained, it's got tiny crystals in it, you can see that it has pretty much the same makeup. It's the same makeup in terms of the types of crystals that we see in the pegmatite as in the rest of the table. It's just that they're smaller. So these had a long time to grow. The system had a long time to cool and grow the crystals. And this part had a pretty short time to cool and grow. So the crystals are much smaller. So you can tell something about the environment that a rock formed in based on the size of the crystals in it, which is pretty cool. When you have a volcanic rock, it erupts and the crystals are very, very tiny most of the time. So even smaller than these ones here. Any questions about this rock? Any thoughts or ideas? Any ideas on where it came from? So somebody thinks it's the same quarry. It's actually not. This one is from just around Fresno. It's still near the Sierra Nevada mountains, but it is, it's just a little bit westward. So from here in Fresno. Okay. We're going to try walking around to the other side of the building now. And we will, if you have questions about this rock as we go along, feel free to ask. Or about other rocks, or I can talk to you about volcanoes. Any questions you've got? So now we're going to the other side of this building called the Mitchell Building. Am I frozen again? Okay. We're going to go down another stairwell, so hopefully this will work. All right. Is that vein in the table gray wacky? So gray wacky is a metamorphic rock made out of a stone called quartzite, and that was not gray wacky. Okay, let's try this. So here we have a rock similar to the one that we just saw. Whoa. No, we don't. All right, let's try that. Can everyone see this? All right, what does it look like? Looks like a sidewalk. Reminds me of concrete. Yeah, so this rock looks like granite. That's right, it looks a lot like that rock we were just looking at from the table. It has some quartz and sand. That's right, and here we can see that it has another one of those gigantic pegmatite veins in it. Does everybody see that? The stripes? It even has veins going all the way to the top. Woo. And so that's very similar to what we were just seeing, but now the makeup, the kinds of minerals that are sitting in those veins are a little bit different. So now we have a bunch of this kind of shiny material. I don't know if you can tell if it's shiny, but this is what's called mica. and it has all kinds of thin layers in it. And mica, does everybody see that? These kinds of thin, shiny layers. So that's a mica, M-I-C-A. And what do we think this gray mineral is? Any ideas? Quartz, that's right. So it's the same kind of quartz that we saw before. Now, when you look at this rock, do you notice, it's kind of hard to tell, but do you notice anything about the orientation of the crystals? Do they look like they're all jumbled up, or do they look like they're kind of in lines? Yeah, so they're kind of lined up. They have what's called a little bit of a foliation or a lineation. And this means that it's been a little bit metamorphosed probably. It's experienced something like high pressures and temperatures, and that's actually created, and it's been pressed, and so it looks kind of like that rock that we were seeing on the other side that had all those lines. But this one isn't, those lines aren't as well developed. So we don't see it quite as clearly, but some of the crystals are a little bit lineated. And here we can see some kind of particularly smushed areas. All right. Is the vein displayed at the same angle it was found in the earth? Good question. So that's hard to say because this particular slab has not been oriented. If we were to have, when this slab when this rock was collected, if we knew which way it was collected, we would be able to kind of know how the vein was oriented. But in some way, shape, or form, the vein does reflect the way that it was in the earth, but I'm not sure if it's being displayed that way currently. So I don't know if this is the angle. You know, this could have been a slab that was put on its side, or it's now facing upward. So I don't know the answer to that, but good question. All right, let's take a look at this rock. Let's see if we can see it. What do you notice about it? Other than my shadow. I see circles, I see geoids, has lots of circles in it. That's right, it's got shapes. So those are called orbs. What this is called is an orbicular diorite, which is big words, but these orbs, any ideas on how they formed? Pattern looks like leopard patterns, that's right. So this rock is sort of similar to some of the other ones that we saw in that it's a magmatic rock. So it's made of, it was made from a magma. And one idea is that in the place where the magma sat in the earth, it was next to some cooler rocks. And in the space in between the magma and the cooler rocks, some hot water came up. And in that hot water, there were rocks incorporated in it. And as they came up, they reacted with the magma around it and formed something new. So the idea is that the centers of these orbs are that initial material that came up in the water. Let's see if I can, so that the centers of the orbs, this part of the orbs were formed and brought up with the hot water. And then the rims around the orbs formed when it interacted with the water and the magma around it. So this is actually a magmatic rock, not a sedimentary rock. So it wasn't formed from water, but it was formed from a magma at high temperature deep in the earth. It's a pretty cool rock. And the formation of it's actually not entirely understood and not entirely clear. So there's a lot of room still for research and interpretation to understand how this rock formed. So if you're interested in geology, I highly recommend checking out orbicular diorites and orbicular granites. Any questions about this rock before we move on? One person likes it. Where is it from? Good question. Let me see if I have a map of it. I think I might not actually know the source of this one. Let's see here. I don't know. I think it's from near the Sierra Nevadas, but I don't know for sure. All right. Other questions? This is an orbicular granite or orbicular diorite. ORBICULAR space DIORITE. Okay, we're going to try to move on. Now we are moving to what's called the Green Earth Sciences building. So the first building we saw, the one with the sandstone, is called the Geo Corner, and it's been there since the place started, since Stanford was built. But the Green Earth Sciences building, where we're going now, is much younger. Okay, somebody said you lost me and that I'm frozen. Is it any better now? Okay. And somebody asked, are all magmatic rocks igneous rocks? Yes, all magmatic rocks are igneous rocks. Okay, we're getting close. So this is the Green Earth Sciences building. And there are all kinds of different earth sciences that are studied in this building, including geology. All right, let's go take a look at the rock that makes this building. Okay, what do you notice? Any observations? Looks like stucco. Yeah, it's got kind of this knobbly texture. It's yellow. Maybe you can see it a little better down here. Sort of tan color. Clayish. It's rough. It's pinkish. Yeah, so it's kind of pinkish gray. Or sorry, pinkish brown. Looks like tan sand. Yep, all great observations. Somebody thinks it might be made from clay. Somebody thinks it might be sandstone again. All very good ideas. This is actually something that we call a dolomite. So a dolomite, has anyone heard of limestone? So limestone, so dolomite, D-O-L-O-M-I-T-E, is a type of limestone that has a lot of magnesium in it, the element Mg. Does anyone know where limestone or or dolomite forms. Limestone reacts with acids, that's true. Caves, seabeds, the ocean. Yeah, so limestone does form in caves, that's true. But the main area limestone and dolostone or dolomite form is in the oceans. So similar to sandstone, it's also forming in the oceans. Given that it's forming in the oceans, do you think we should find fossils in this limestone, in this dolomite? One person says yes and one person says no. Maybe, that's right. So yeah, so there are oftentimes you can find fossils in limestone or dolomite. But this one has been there have been so many critters going through it that it's actually disrupted the layers of the rock so much that it has this kind of mottled texture to it. So oftentimes if you find limestone or dolostone and you look around, you can often find fossils, but in this one, we unfortunately won't find fossils. Any idea where in the country this dolomite comes from? Where the quarry for this dolomite was? One person says California. This dolomite is actually from Minnesota. So they quarried all this dolomite to make this building and they brought it all the way from Minnesota. It's a pretty far way to go. All right, any other questions about the dolomite? If not, we will head to our last place on campus, which is also outside the Green Earth Sciences building. You can see there are lots of rocks sitting outside of it. So let's go ahead and take a look at this one. What do you notice? Has a little green on it. Some people are saying it's a granite. What makes you think it's a granite? It is indeed a granite. Here's the polished face of it. So maybe you can. I'm back now. Sorry. Hopefully you can see the video. What kinds of colors do you notice here? Any ideas what minerals we have? Gray, black, white. Yep. So that's kind of the quintessential. That's how we kind of describe granites relative to, say, basalts. Basalts, which come out of Hawaii, are black, they're dark, and granites are white. And that's because they have a lot of quartz and they have a lot of feldspar in them. So that's kind of the gist of what I was going to show you. And these granites also come from the Sierra Nevada in the mountains just west of where we are here. So with that, I will go ahead and answer any, I'm happy to answer any additional questions you might have, whether about the rocks that we've seen today or about geology and rocks in general. And otherwise, I think our session is coming close to the end. Yes, this rock is from California. And I hope you learned a little bit about geology and had a good time. You're very welcome. Can granite be all black? Not usually. Usually that's something either a basalt or something like what's called an andesite or a dacite. It's kind of an intermediate rock. They're one rock that's most common throughout the world, throughout the US. So the most common rock is basalt that makes up the ocean floor. And the rock that makes up the continents is mostly granodiorite. How does rainbow obsidian form? So rainbow obsidian forms when it's an obsidian. I think this is rainbow obsidian. It has lots of tiny, tiny crystals that we can't see with our eyes, but we can see them under a microscope, and they kind of create a little holographic effect when it interacts with the light, kind of like a prism, because it has all these tiny, tiny little crystals in there. Where do I do most of my research? I do most of my research here at Stanford, and I use machines, but the volcanoes that I study are from Nevada and California and New Zealand and Antarctica. All right, I think that we are just about at the end of time here, and it was really nice to meet you all. And I think Sabine has a little bit to say at the end. And yes, I did get to go to Antarctica.